I'm Charlie Club. We'll probably hear from some of our officers later on. But as tradition would have it, we always have our guest speakers speak first. But before I introduce Fred, I do have one announcement to make. We just discovered that it is Joy's birthday today. So how about everybody, happy birthday, Joy. And she's taking minutes on her birthday too. Tried to get out of it, but didn't work. So. Oh, okay. Adrian took the minutes away from Joy since it's her birthday. So, okay. So with that, we have the return of one of our favorite speakers and also an honorary Lowbrow member, Dr. Fred Adams, who actually worked in the physics department, but he specializes in astrophysics, especially star formation, cosmology, and the early universe. Fred received his Bachelor of Science from Iowa State University in 1983, and he earned his PhD from the University of California, Berkeley in 1988. But we're really honored to have him right here at the U of M with us. So Fred is an internationally recognized expert in several fields, the author of many papers, and I knew of 2 books. Weren't you working on a 3rd one, Fred?
I'm thinking about it.
Okay. So 2 and some percentage books. But anyway, with that, I'm just going to go ahead and turn it over to Fred so we can get on with what he's going to lay on us tonight, which is the future of computation. So with that, please welcome Dr. Fred Adams.
Well, thank you. Thank you, Charlie. Thank you for the entire group for having me back again. It's always great to see you guys, even under these not quite so ideal conditions. One note, those of you who are not speaking, you might want to mute your thing because the recording will work better that way. And thank you. So the talk I'm going to give today is a little bit of a departure from the kinds of things I've talked to you about before. And not to worry, I will work my way back to astronomy at the end because that's what you guys are all here for. But hopefully this will be of interest to you more generally than astronomy, even though of course astronomy is the best thing that we can all do. So an outline of what I'm going to talk about is here. First of all, I'm going to start by giving you an entire history of science, just for a couple of minutes. And then what I'm going to use that for is to make the point that there's an exponential growth of computational resources of all kinds. You've probably heard of Moore's law, but Moore's law is just the beginning, okay? So I'm going to outline that. And what we'll see is that that's going to put limits on computation and science going forward, and it will also set up some future challenges. And then hopefully this will spur a bit of discussion so we can have a little bit of fun throwing some ideas around at the end. So start with a history of science. So let's begin in the beginning. The beginning of science, I think, kind of happened in the time of the ancient Greeks. So if you go back to the time of Plato and Socrates and Aristotle, the intellectuals did everything. They were the philosopher kings. They did physics, which was science. They did metaphysics, like philosophy. They also did ethics and politics. So the Platos and Aristotles of the world did everything, right? Then if we dial forward to a little bit later in time, we kind of separated the sciences from all of the rest of intellectual activity. In the very first universities in Europe, there actually weren't science departments, which is kind of interesting. The university predates the existence of science as a discipline. But Galileo, for example, was one of the guys who was the shot heard around the world. But the Galileos of the world, especially people like Galileo, did everything. Galileo needed a telescope, so he invented a telescope. He needed to do some calculations, so he did some calculations. He actually did some experiments, and so on. So he kind of did all of science, or at least all of physics and astronomy. Now, for most of what I think people in our generation, because you guys are as old as me, I think, mostly, what we tend to think of when we think of the sort of disciplines of science is that we kind of divide them into 2 bits, experimentalists and theorists, right? So the specialization is that the theorists do the calculations to work out what should happen, and what the theories say, and then the experimentalists go and they measure things to see if that is in fact the case. Now, from the astronomical side, we replace the experiments with observers. So the experiment is to actually look at the sky and see what the universe is doing, see what stars and galaxies are doing, and report back. But there's been, I think, for the last century or so, or for nearly a century, mostly the 20th century, there's been this sort of cross between observations and theory, or experiment and theory, and that's been kind of the two camps. Now recently, and recently means the 90s, this split, because in addition to experimentalists and theorists, there was a new discipline that kind of emerged. People like my friend Gus Everard, who I think has spoken to you before, became numericists, right? They do numerical experiments. Now they do numerical calculations, which are sort of like theory, but they also just set things up on their computer and see what happens. So they're kind of in the mode of doing experiments as well. And that's kind of a new mode of thinking. And now we have sort of three things to keep in mind. And then, if you've read a newspaper in the last couple of years, there's yet another split. There's now this new breed of scientist worker called a data scientist, right? Googles of the world have kind of driven this. And now there's really four disciplines. So my first point, and I do have one, is that if you look at the history of science, for like, in the beginning there was philosophy, which is, by that I mean not just what we now think of as philosophy, but sort of intellectual activity, the Platos of the world. Then science branched off, and then physics branched off from science, and all of that took about 1,000 years, order of magnitude. And then for the 20th century, we had experiment and theory. The two camps, they went back and forth and both fought and collaborated, and we had good interplay. And then in the 90s, it split into experiment, computation, and theory. And that all lasted for order of magnitude a decade, maybe two, depending on how you do the boundaries. And then we have four things: experiment, big data, or data scientists, computation, and theory. So my first point is that what's going to happen next? You also see two things. One is that things are going to happen. There will be new branches, but also there's a certain acceleration. We had sort of science and physics for 1,000 years, experiment and theory for 100 years, computation for 10 years or maybe 20, and now we have four things. It will not be long. So the first thing that you should keep in mind is that there will be a new paradigm. And this new paradigm is going to come sooner rather than later. So it's kind of interesting to kind of get ahead of this and sort of see, well, what's coming down the pike, right? Now, I'm now going to switch gears a little bit, and we're going to talk about computation in a little bit more detail. So when we talk about computation, what we want to do is we want to outline the exponential growth of 5 things. It's not just Moore's law. But when you're talking about computation and the science that goes with computation, you can consider the volume, how much data you're processing, or the data doesn't have to be real data, it could be like made up data or theoretical data. The velocity, as in your computational speed, the variety, and also the veracity and the value. These latter two, which I'll only talk about briefly, are sort of not as often considered, okay? So this is what you're used to thinking. If you look at the transistor growth, this gives you Moore's law as a function of time. So the amount of transistors you can put on a circuit board, which is kind of a measure of the just the number of computations you can do on one little chip, has been growing exponentially since, well, in this case, since 1970, but it really was growing exponentially before that. And it's a nice power law. It's a power law with a doubling time of about 2 years. Now, if we look at not the number of transistors, but we look at the speed at which computers work, the number of flops per second, or we measure it in very large numbers of flops, we see that we also see exponential growth. Now, if you look very, very carefully, and I'll help you guide your eye, what you see is that the overall growth rate here is nicely exponential, as followed by the orange line that I put on top of it. But is starting to dip below that. And that's, for now, not a big deal, but that might be a harbinger of things to come. So we have the total number of chips growing exponentially, the speed at which they operate growing exponentially. We also have another point, another aspect of this, which is the volume. In other words, if you're going to do computation or take astronomical data for that matter, you got to put it somewhere, right? Now, where do you put it? Storage. So the amount of storage that we use human race wide is also growing exponentially, okay? So the volume of storage is growing exponentially. And it's growing exponentially with kind of sort of the same rate, okay? So we have speed, volume, number of transistors, all growing exponentially with the doubling time of not exactly, but close to 2 years. Now, what else grows exponentially? Well, you've probably heard of the stock market. The stock market grows with a doubling time of 7 years, or 7 to 10 years, depending on how you fold out what you say about inflation and whatnot. But it does double, it does grow exponentially. So it's like the other exponential growth laws we're considering, but significantly it's slower. The doubling time is longer, which means it's not growing as fast. Now, when you read the newspaper or listen to people on the radio talking about the economy, the first point they make is that the stock market is not the economy is not the stock market. So what you should do is plot the two on top of each other. So here's the GDP versus the stock market. They both grow exponentially at the same rate. So in that sense, averaged over a century, the stock market kind of sort of is the economy, and the economy kind of is the stock market. The difference is that the stock market has these huge crashes and dips and bubbles, and there's a lot of noise in the stock market. So just because it's going up or down 1 year is not really necessarily significant. It's significant if you lose a lot of money or gain a lot of money when you sell at the right time, which is of course what the game is. But in terms of like how things are operating, you need to average over all those wiggles. And in that case, both the stock market and the GDP are growing nicely exponentially with a doubling time of, let's say, 7 years, okay? And there's more. If you look at astronomical data, the variety of data that we get is also growing exponentially. Now, it's hard actually to put an exponential curve on this, but one of the things that we see is that, I'll just go to the next slide. One big breakthrough in the 90s was the Sloan Digital Sky Survey that had a huge amount of volume, and we were taking data at incredibly high rates, as shown on this plot, of 200 gigabits per day, right? In the 90s, that was unfathomably large. But now look, then we went to Gaia, which is operating now, and now we're doing even more. But the things that are coming are Pan-STARRS and the Large Synoptic Survey Telescope and the Square Kilometer Array. These are big mega collaborations. And the amount of data and the volume of data they'll get and the rate at which they get those data and the different kinds of data that they get are all growing enormously. Now, this one doesn't have the beautiful graph that I could show as an exponential law, but the variety is also growing, okay? Now, what else grows exponentially? Well, if you're a cosmologist, or at least one brand of cosmologist, what you do is n-body simulations. N-body simulations are a way to observe or to simulate the entire universe to look for the formation of structure, the formation of dark matter halos within the structure, and even the formation of galaxies within those halos. So one thing you can do is plot the number of n-bodies that you can do in your computer as a function of time. Just to date myself, right before I came here, I was in Cambridge, Massachusetts, not England. And my friend Ed at MIT said, oh, I can simulate 1 million particles in my n-body simulation. And he was all excited because that was the first time you could do 1 million particles, right? Now you can do 1 million particles on your phone. If you were to use those computer chips to like run a little program that, like the ones we were doing in 1990 or 1991, you have enough computing power on your phone to do those kinds of simulations and more. Your laptop is crazy better than that, right? A million particles is just nothing. Now we go all the way up to trillions of particles. And you can make beautiful simulations like this one shown here that give you more and more and more detail. So what we have, and the point that I'm trying to sell you, is that when you look at computation, specifically, I'm interested in the computation we might do in astrophysical problems, but this holds, more generally than that. Everything's growing exponentially. Volumes are growing exponentially. Velocity, the speed at which you can compute, is growing exponentially. The number of things that you can study are growing exponentially. Significantly, the economy is also growing exponentially, but computation is doubling faster than the economy. So computation is outpacing the economy at the present time. Now, it's also true, and this is one of the food for thought that I want to leave you with. Don't worry, we're not done. But I want to leave you with is that computation in its many guises is one of the most important drivers of the current economy. What are the companies that are driving this? Google and Amazon, they're all online companies, right? So what we're going to talk about next is how long can the party keep going? And my point is, to give away the ending, not as long as you think, okay? And this will have important ramifications for the economy. If the economy is currently driven by computational things, and computational things must slow down or saturate, then there's going to be a reckoning. Either the economy will no longer grow exponentially, and then the entire business model of every nation has to change, because it's all built on exponential growth, or we have to have something that replaces computation to keep the exponential growth party going. And there's really no escaping this. The only question, I think, is how long do we have before the saturation happens? So just to pose the question, given that velocity and variety and all these things are growing exponentially, what are the limits? So what we're going to do next is we're going to do some extrapolation. Now, before I do that, you got to be careful. When you extrapolate, you're sort of assuming that what happened before will continue to happen in the future. So one good example of what could happen is that suppose you have data that goes from, as shown in these blue data points, if you fit a line to it, then you have an extrapolated curve that goes up and up and up and up. But the red curve, which is more of a sinusoidal curve, in this particular case, fits the data just about as well as the line. So if you extrapolate and you don't know the true function underneath, you could get a very wrong answer. So with this warning, we're going to now proceed to ignore this warning and simply extrapolate and see what we get, okay? So let's start with storage. We saw that storage is growing exponentially, right? So let's do a little calculation. Okay. The mass of the biosphere is about 1 trillion tons. So if I put that in grams, it's about 10 to the 18 grams. Okay. Well, when you store data on your phone or your laptop or a hard drive, you get about 1 terabyte per kilogram, which is about 1 gigabyte per gram. You get 10 to the 9 bits, or bytes rather, per gram, okay? So if I could use the entire biosphere, which is just a benchmark, as a hard drive and store data, the total amount of bytes that I can share is about 10 to the 27 bytes. Now, currently, we're actually using about 10 to the 22 bytes planet-wide. We're only a factor of 10 to the 5 off. That's 16 doubling times. That's 32 years. In other words, if we continue at the current pace, and we continue to having to store more stuff on hard drives without any brand new technology, in 32 years, we'll have more of the resources of the planet involved in storing things on hard drives than the entire biosphere. That's kind of a sobering thought. And the biosphere is kind of an interesting benchmark because that's kind of everything we got, right? As soon as you have more volume and stuff than the biosphere, things have to change. Now, that doesn't mean they can't change and they can't be made, but it's a big problem that we as humanity have to solve. Now you might say, well, we can get more efficient. The hard drives that we have are kind of inefficient. What can I do? Well, the most efficient you possibly could be is to take all the particles in the biosphere, of which there's 10 to the 42, I counted them. And you can say each particle, each nucleus can have spin up or spin down or something. And that's a 1 or a 0, which is a bit. So a byte is 8 of them. So the whole biosphere corresponds to something like 10 to the 41 bytes. If you could use each particle as a 0 or a 1. Now, with that many bytes, you would still run out of storage space in 126 years. Now, it's longer than 32, but it's not that much longer, right, in the grand scheme of things. That's the power of exponentials. If you keep exponentiating everything, you eventually run out, okay? Now, this is just the storage. The other key issue, going back to the number of transistors that we're using, we talk about Moore's law, as in, we have this computational power that is continuing to be exponentially growing. What we don't talk about, because it hasn't really arisen, but it's rising right now, is that it costs a lot of money to power all those computers. So let's do this calculation. Suppose you want to do computing not at the current slow rate, but at the maximum possible, most efficient rate. Well, you can work out that if you want to flip a bit, which is like making 1 0 into 1 or a 0 or 1 into 0, the most energy efficient you can be is log 2 times kT, where T is the temperature, okay? That's the best you can do. So let's take the entire budget of the Earth. The Earth gets 100 quadrillion watts, which is 10 to the 17 watts from the sun. That's the power, that's the rate at which our planet is being powered, right? So the theoretical maximum computation rate is at the temperature that it operates at, which is basically room temperature. The maximum computational rate is this number, 7 times 10 to the 37 bits per second. So right now, all the computers in all the world are mostly looking at cat videos, but what they are actually doing is they're burning about 10 to the 25 bits per second. And again, I think 90% of that is cat videos. But no matter what it is, that's what they're using. So that means you have a factor of something times 10 to the 12 before the energy we use for computation is bigger than the energy we get that's driving the whole planet. That's 43 doubling times, which is 86 years. So, in other words, in 86 years, the amount of energy we use for computation will be greater than the amount of energy that the whole planet gets from the sun. And in this case, I'm using the maximum possible numbers of bits per energy that you can get. That's the theoretical maximum. Since we can't actually reach the theoretical maximum, that will happen sooner. Or, but the other alternative is that we can't keep growing the computation that fast. But if we keep growing the computations at the rate we have, you've got less than 86 years before you run out of energy. Now we could do the same kind of extrapolation for our n-body calculations. For the n-body calculations, the doubling time is actually a little bit faster. It's only 5/3 years, a little bit less than 2 years. That's because in addition to the computation power going up, the people who do these are getting smarter and they can write more efficient algorithms and such. So we can do the same kind of extrapolation we did before. The current capability of n-body calculations is about 10 to the 12 bodies. The Earth's biosphere has 10 to the 42 protons, as we saw. So in 150 years, if n-body simulations were to grow in the number of bodies that you could do, you could simulate one particle in the biosphere. In other words, you could make an n-body simulation big enough that n is as big as the number of particles in the biosphere. So you could actually simulate the biosphere on a particle by particle basis in 150 years, okay? So the lesson here is that we have exponential growth of all the computational metrics. And the easiest ones to sort of keep in mind are the speed at which we calculate and the amount of stuff we put in silicon to store, right? Both of these are growing exponentially with the doubling time of order 2 years. And we see that both of these must saturate in relatively short amounts of years. The amount of mass we put into silicon storage devices will be bigger than the biosphere. And the amount of energy that we need to drive all these computations will be more than the energy the whole planet gets from the sun. Now, admittedly, all of these calculations I'm giving you are resting on assumptions, they're extrapolations, there are uncertainties, a lot can happen. As I think Yogi Berra said, predictions are hard, especially about the future, right? But at the same time, we've done several different versions of this calculation. And the time of saturation when you run into trouble is of order 100 years. It's not 1,000 years. It's not 10 years. It's tens of years or up to 100 years. So in 100 years' time, something has to give. We can't just keep growing exponentially the way we do computation. We can't just keep putting more stuff on silicon. We can't just keep calculating faster and faster. If those are the drivers of the economy, then the economy has to change or it has to saturate. When the economy saturates, you call it stagnation, right? And that people think of as bad, okay? So what do? Well, we need something, and those things we need are energy sources, new storage strategies, new algorithms, or just a new paradigm. Now, unfortunately, I have to come clean. I don't have the answers. I'm only going to give you the problem, okay? Now, there's a little bit of hope. If you go back to the 60s and 70s, and I'm guessing most of you remember the 60s and 70s. It depends a little bit what you were doing in the 60s and 70s. But one of the things that people were worried about back then was overpopulation, and for a good reason. The population is growing exponentially. And if you looked at the projections, especially back then, they were pretty dire, because if the population kept growing at that incredibly high exponential rate, there would just be so many people, it's hard to feed them and such. Now, what happened, of course, was that the population is continuing to grow, but it's starting to saturate. So there's hope that we're not going to reach that exponential overcrowding of the planet. So that's a lesson that maybe we can get by with a saturation of computation, but we'll have to live with that some way. Now, there's yet another aspect to this. One of the greatest science fiction plot devices is that robots and computers will take over the world, right? One way or another. There's different guys to do this. I'm guessing some of you have seen some science fiction, right? So one of the things that people talk about is the so-called artificial intelligence singularity or the AI singularity. And the idea is, it's phrased in a bunch of different ways, but the idea is that computers are getting smarter, okay? And right now, computers can do certain tasks a whole lot better than we can, but not everything. So right now, computers are not smart enough to take over the world. They're smart enough to do a lot of useful things for us. They're smart enough and involved enough to actually mess a lot of things up. But right now, the computers are not off in computer land plotting against us. They haven't figured out how to plot yet. Now, the worry is that they will, right? Now, here's the thing. Right now, in spite of the enormous amount of computation that we have, the human brain can compute a lot more. So right now, we're ahead. We're ahead of the computers. But humans are kind of saturated. We're not getting smarter. Some could argue we're going the other direction. But let's be optimistic and say, well, we're just fine. We're all good. We're just here. We have a certain amount of brain power. That brain power is good, but we're not growing. We're not doubling our computational power every 2 years. We're just not. I mean, as a species, right? Charlie might be, but the rest of us, we're lagging behind. So if computers are growing and humans aren't, the computers are going to win at some point, right? So I'd like to make 2 points. One is that let's see where we are now. Well, right now we're sort of at the following place. If you take one of the state-of-the-art computer programs called AlphaGo 0, it can actually beat people at Go, including the best people who play the game Go. This is also true of chess, but Go is a little bit more computationally complex, so that's what we're using. Now, the AlphaGo computer burns about 3,444 watts, okay? The person it plays against, by comparison, is burning about 100 watts. So in order for a computer to beat a person now, the computer has to burn about 30 times more energy. So if the computers wanted to fight against us and conspire against us, how far down the path are they? Well, now, if you had a computer for every person, and the computers had 30 times more energy than the whole human race, they could beat us at Go. That's where they are. That's not taking over the world, because Go is a very mathematical game. It's kind of humbling to have everybody in the human race be beat by a computer at Go. But at the same time, the world doesn't end. We just lose the game. But the worry is that they'll get better. And they get better and better and better. We're saying the same. There will be a singularity, the time at which the computers can outthink us in all ways. Now, there's 2 ways we can mitigate against this. One is that if this singularity, where the computers are smart enough to take us over, is more than 100 years in the future, then we win, because we won't have enough computational power, which means the computers won't have enough computational power to keep doubling fast enough to beat us. So one way to stave off the so-called AI singularity is that it never happens, because the computers saturate before we reach the singularity. Now, there's also the chance that we'll come up with energy sources, efficient algorithms. Maybe the computers themselves will teach us how to do better algorithms, and they'll reach the singularity before we run out of energy, right? So then what you got to do, and this is the lesson for today, here's the solution. You unplug it. Now, this is sort of a smart ass way of saying things, but just like when we have dangerous viruses in labs, there's protocols that you don't want them out in the wild, right? If you were ever able to build an artificial intelligence program, you should not connect it up to the internet. You need to firewall it, right? Now, that's going to be hard, right? People are not good at these kinds of things, but that's what we got to do. So it's good for, since we're actually a ways away from the singularity at the moment, it's kind of good to keep these protocols in mind sooner rather than after the fact, right? So my main point is simply that we're racing for this AI singularity. And the key question is whether we saturate first or not. So the summary to date is that computation is this new paradigm that's led to a new branch of science in computational science, a second new branch of science in data science. It's revolutionized a lot of things. It's revolutionized a lot of the way we do business, the way we live our lives. You know, I use Google Maps a lot, right? I don't know about you guys, but you know, it's a lot of good things. But the revolution will be delayed, and the revolution will have limits because all of these exponential growths that we are now seeing can saturate if we don't do something, right? And that poses a lot of challenges. Ah, yes, sir. Well, if we run out of energy, we won't be able to like do the television, right? So, okay. So there's a number of challenges. So we need to overcome energy limits and storage limits. And also there will be a new paradigm shift. So it will be interesting to sort of consider what that's going to be. Now there are ways to mitigate these things. So one way to mitigate these things is that I've sort of arbitrarily said that the amount of computation, energy we have for computation is that we get from the sun. But that's not really a hard and fast limit. That's just a good benchmark to compare to. So how can you go about getting more energy than we get from the sun? Well, in the long run, you can't burn any fossil fuel like coal or natural gas because where does coal come from? Plants, which come from the sun. So in the very long term, you're never going to have the planet make enough coal to beat the amount of energy you get from the sun, okay? But what you can do, and I'm not like a big zealot for nuclear power, but it's just the one solution that we have. You can make breeder reactors, which will breed nuclear fuel. And then you can burn the nuclear fuel, getting more energy than you use to breed them. And that will give you a way to beat the limit of the amount of energy that you get. And zero greenhouse gases. Now, it can even be made very safe, which is a separate talk, if you're smart, if you're careful. Those are two big ifs, but nonetheless, they're possible. Now, for the computational side of things, you can gain a little bit of time before the saturation if you get more efficient. You can get more efficient algorithms, which lets you do more computation for the same power. You can get more efficient storage, so you can store more for the same amount of mass, and you get more efficient computer architectures, so you get more bang for your buck that way. The other thing that most people don't really consider is that if you develop the analytic mathematics, you don't have to compute as much in the first place. This is more of a technical thing for people in my field because everyone has sort of abandoned analytic development because computers are so cheap. It's easier just to like throw a computer at the problem. That's why I put the little dinosaur there. Only dinosaurs like me actually still do analytic calculations. But nonetheless, I think when you run out of computational oomph, you have to go back to the basics, and the analytics can be an important thing. We can talk about that more if you want. So this is all kind of a little bit pessimistic. So I'm going to now change gears once again and give you a solution. And this, hence the caution sign, is both fun and totally ridiculous, okay? So hold on to your hats. How do we actually solve, very good. How do you actually solve this computational issue? Well, most of you have heard something have you guys heard of what a Dyson sphere is? So the idea of a Dyson sphere is that you put a sphere around a star and you steal all its energy. And Freeman Dyson put this idea forth in the 60s, I believe. I know he put it forth, I think it was in the 60s, hence the name Dyson sphere. So how do we do that? Well, what you can do is you can build what we call a black cloud computer. And you basically build a Dyson sphere around a star. Now it turns out the best way to do this is to pick a star that's kind of on its way out, like a red giant, okay? For two reasons. One, the red giant is at the 10,000 times brighter than the sun, so you get a lot of energy. But two, the red giant has winds. And the winds are coming out. What's in those winds? Silicon and graphite. What do you use silicon and graphite for? Your computer chips. So what you can do is you build a framework around a star, and you have this computational layer, which is kind of like a modern day Dyson sphere. You mine the silicon and graphite as it comes out, and you build it into computer chips, and then you can use the entire layer for computation. And if you do this, you get an enormous increase in the amount of computation you can do. Now, just for fun, we work this out. You have to satisfy things like the second law of thermodynamics, which puts a limit on how much computation you can get, but it works and you still get a lot. You also have to worry about communication across the sphere, and you can't go faster than the speed of light or not. So that puts another limit on things. But even with those limits, you can get vastly more computation out of what we'll call a black cloud computer than you can for using the entire energy source of our planet, right? The basic idea is that instead of having a planet which is subtending it or stealing a tiny fraction of the sun's energy, you have a sphere which is taking all of it, and then you put it around not a regular star like ours, but a red giant where you get 10,000 times more energy. Now, the reason why we call this a black cloud computer is that it looks like a black cloud. So you can actually put them into a color diagram, and we could actually see them. If they were there, you could actually see these things in the sky with the very latest astronomical observations. So far, we haven't found any. But the point is that if this were the solution, advanced civilizations would build such things, and they would basically radiate like really cold black bodies, hence the name black clouds, and they would show up in the color diagram here. So in this diagram, the various real astronomical sources, stars and spiral galaxies and quasars, and AGB stands for asymptotic giant branch star. Those are real data for real stars, for real astronomical objects that we see. The black cloud computers would then be off to the right of this diagram. They're very much observable, but we haven't found them. But that might be the way forward. So this is sort of a good place to stop, and I will take questions, and we can discuss all of these issues to the extent you'd like to.
Well, since you were just mentioning that, I did read a while back that there was a star, but there was some suspicion that perhaps we were witnessing a Dyson sphere construction. Had something to do with the way the star was slowly dimming.
Oh, well, there have been a couple things. What you might be referring to is this. What we've been looking at to find planets are what's called the transit effect. So if you have a star and a planet passes in front of the star will go dim. So it turns out that it goes dim, or it gets dimmer by sort of 1%. So you guys with your telescopes, if Michigan would ever have a clear night, could probably see this, right? You're shaking your head, but so actually amateur astronomers could see transits around near stars, okay? So astronomers all over the world are looking for planets by the transit method with various experiments and whatnot. What they found though, and when you see a transit, what you see is that suppose it's in a 4-day orbit. Every 4 days, that's not very good. Every 4 days, the light curve looks like this. So this is brightness versus time. Then every 4 days it dips again, and every 4 days it dips again. You have to figure out it's a 4-day period and then fold it every 4 days so that it looks nice and pretty like this. But what they then found was they found a star that was getting brighter and dimmer, but not with a beautiful pattern like the one I drew here. It was kind of a mess. And the interpretation that they came up with was that it's equivalent to having basically a bunch of space junk floating in front of the star. Sometimes big pieces of debris, sometimes smaller pieces of debris, just junk. And then you'll see a very erratic light curve. And what they found was consistent with that. And then of course, that's what the observation was. Then of course the speculation is, oh, well, this is like some civilization that blew something up or making a Dyson sphere or whatever. So, but the evidence was simply this weird light curve from a star. But it was not a planet. It wasn't doing this beautiful thing. So, yeah. Oh, that's a very good point. And the answer is maybe, right? So the idea of a quantum computer is the following. In a regular computer, you work on bits. So you have a bunch of cubby holes. Each one has a 1 and a 0 in it. What you do is your computer program takes those bits, flips them around from 1 to 0 or 0 to 1, and puts them back in the cubby hole. Repeat until you do everything that you do computationally is built on those building blocks, okay? So the fundamental thing is a bit, which is either a 0 or a 1. And if you think of it in terms of like particles, you could represent the 1 with the spin up and the 0 with the spin down, which are two states of a particle, okay? Where does quantum mechanics come in? Well, the beauty of quantum mechanics is that you can be in more than one state at the same time. See, like when I flip a coin, it's either heads or tails. But if I flip a quantum coin, I can make it so that it's partially heads and partially tails. I can make a quantum bit, which we call a qubit, that's partially a 1 and partially a 0. And that means there's an infinite number. And since if you're partially 1 and partially 0, you can have any real number between 0 and 1 as the fraction of oneness and the fraction of zeroness is then set. So you change the bit from one piece of information to a lot more information because you have this continuum of possibilities all in one little bit, which we call a qubit. So that's the first step. For certain classes of computation, certain kinds of problems like code encryption, you can build algorithms based on this idea that are a lot faster, enormously faster than algorithms based on zeros and ones. So that's good news and bad news. It means that for certain classes of computation, if we could ever build a quantum computer that worked, we could do that class of computation enormously faster, and that would make this singularity go away. There's 3 problems. The first problem is we can't build one. Right now, you can build 1 bit that will last for like an hour. That's where we are. 1 bit that lasts an hour is nowhere near what you need for gazillions of bits that will last for long enough to do a computation, right? Now, hopefully we'll make progress, but we just don't have the technological way to do it at the moment, okay? The other issue is that so far, and again, so far, we've only identified a few problems where you can actually employ a quantum computing algorithm to get this enormous speed up. The kinds of things that I talked about for in-body simulations and astrophysics would not be sped up this way. Now, we're not done, we're just starting. So people are clever, they will come up with things to do, but it's not guaranteed that you can do all of computation fast. Now, on the other side, and this is the third thing I want to mention, the one thing that you can do fast is code breaking. At least the way we now do encryption codes, that the algorithm to break those encryption codes is the thing you can actually use a quantum computer to speed up the computation enormously. Which means as soon as you do build a computation or a working quantum computer, all codes are broken. There will be no security anymore. Or the people doing security will have to come up with a new algorithm. So they should be working on that now.
Somewhere I heard that there were ideas being talked around using
Yeah, they're working on it. I think they need to work on it more. It's very important. But maybe the quantum computing landscape will improve. I would have given almost the same answer about 10 years ago, which is when I first heard about this kind of thing. So the amount of progress we've made in 10 years has been, well, I mean, from a scientific point of view, it's been great, but in terms of how close are we to building a mousetrap that works, we're still pretty far away. Now, of course, once there's a breakthrough and things work, all of a sudden, you know, things happen, right? So that could happen anytime. But right now we don't have them. So yeah, so I wish I knew more about this. It's a very interesting topic, but I've just downloaded everything I know. So I'm kind of done. Yes, sir.
For you personally, what sort of the holy grail of n-body simulation?
Well, I don't actually do n-body simulations for a living, so I don't really have a holy grail, I guess. Maybe you want to ask a slightly different question, or I'm not sure. I'm not exactly sure what you're getting at. So,
what would be the most interesting problem of going back to the Big Bang and back the origin of the asymmetry? What would be the first problem you want to solve?
Well, let me answer this a couple different ways. The key stumbling blocks and the things I really want to understand are not computationally limited. You put your finger on a couple of the most important things. If we go back to the early universe, one of the things that we really want to know the answer to is whether there's an asymmetry between matter and antimatter. If you look around the room, it's all matter, right? Touch the table, you don't explode. It's all matter. We can do that experiment around the universe, and the whole universe, everything within our cosmological horizon, is apparently matter and not antimatter. So at the present day universe, everything's matter. Going back to the early universe, something set up an asymmetry so there's more matter than antimatter. Now the asymmetry is not as big as you think, because back then everything was in the form of quarks. For every 30 million antiquarks, there were 30 million and one regular quarks. All the antiquarks annihilated with the quarks, the 1 part in 30 million quarks combined to form protons and neutrons, and then presto, we're here, okay? There's a few steps missing, but that's the general idea. Okay, key question, what sets up that asymmetry? So I would love to answer that question, for example, but what I need to answer that question is really an extension of our understanding of the laws of physics that allows for what's called baryon number non-conservation. And that's not limited by my number of n-bodies. It's just limited by we don't have the right physical theory to do that. Now, once we do have the right physical theory to do that, then there will probably be some computation to be done. But the key thing there is the missing physics, not the missing computation. Now, another thing I'd really like to know is that if we go all the way back to the Big Bang moment, I mean, careful to call it a Big Bang moment, not a Big Bang. You get to the realm of quantum gravity when you can't actually define time to better than 10 to the minus 43 seconds. And you can't define space to better than 10 to the minus 31 centimeters. That's the realm of quantum gravity, where quantum mechanics and gravity have to somehow interplay. String theory and its descendants like M theory are constructed to understand that physics. Right now, we don't. And what I mean by that, again, tremendous progress has been made, but we can't actually do the one thing we want to do, which is write down a theory that tells you how you launch the universe. Now, once you can write down a theory that tells you how to launch the universe, that problem will require serious computation. And I would love to put a computer on that and simulate that quantum mechanical tunneling into existence that will happen at that Big Bang moment that launches our universe onto the trajectory that gives us the rest of the Big Bang. That's what I'd love to see. We're a ways from that. Both, we don't have the theory to do the equations, and then we don't have the computation to do the simulation once we've had that. So we're missing kind of a large fraction of my wish list there. There's other things I could name, but I think that would probably be the ultimate thing.
We have questions from the Zoom audience.
Well, I think going from binary to trinary or other would be only a modest change. If you could go all the way to a continuum of things, then you're in the quantum computing realm. And then for, like I say, certain problems, that would actually give you a nice efficiency or savings, but only for, as we know, as of what we know so far, it only gives you that savings or that added efficiency for certain classes of problems, not for every problem. But there might be some more algorithm development that can be done. All of these things are in the whole quantum computing business is really in its infancy. So, you know, things might look very different 10 years from now. So I should also come clean. I'm not an expert on quantum computing. So of all those things Charlie listed at the beginning, quantum computing was not on your list. So it's fun to talk about. It's interesting to talk about that. Any other questions from you guys?
One thing I keep hearing is people who are creating Bitcoin relative to the economy. I've heard that people are mining Bitcoin and have to use power and because it's competing source them.
Well, I think everything you just said is pretty much true. It costs an enormous, it's very computationally intensive to find a new Bitcoin because the Bitcoins are a special mathematical thing and each successive one is more computationally expensive than the last one. So the easy ones have been found and it's kind of like finding a bigger prime number, right? Only it's a harder thing. You know, it's easy to go 1, 3, 5, 7, 9, 6 per mill error, 11, and you know, but as you go like to 6 and 7 and 10 and 100-digit primes, it gets harder and harder, right? So in the same way, when you looking for Bitcoins, you're looking for patterns in some crypto space. Each successive one is more computationally expensive. So where we are on that business is that it costs an enormous amount of time, money, energy, heat to do the computation to get a new Bitcoin. So it is in fact a drain on the system. Everything you just said is right. So I don't know the exact percentages or the numbers, but it's enough to be significant. It's also enough of a problem that for a while, you know, graduate students at various universities will say, oh, well, I'm going to get rich and like hijack all of the department's computers to look for Bitcoin. they are now strictly forbidden from doing that because it eats all the resources, and those guys are fired immediately. It's kind of a waste of resources. And it also eats up everything else, and you can't do any science with it. So it is a very computationally expensive thing. To find Bitcoin, you would have to hijack like the physics department's whole set of computers, right? Which they do not want you to do. Yeah, I think that was that might have been more of a copyright thing, not a computational resource thing.
Oh, right. The idea of hijacking science computers.
Yeah, that's a no-no. Yeah, that's true. That's a good point. Oh, okay. So, aha.
I have a question.
Okay, go ahead. I can hear you for the moment.
Yeah, do you think that Dyson Sphere that you envisioned that basically absorbs all the energy from that star and converts it into computational power, is there room there for a biological civilization, or do you think it just became a giant AWA that absorbed its creators?
Oh, well, I think as long as we're speculating, it could go either way. There's certainly enough real estate and energy in that sphere to have, you know, a colony or a population. It's much bigger than Earth, so you could certainly have an Earth-sized population living in that layer in terms of the energy resources and whatnot. Now,
Sure,
whether or not people will cooperate in a way to do that or not is, I think, the big question. But unfortunately, I don't know anything about that. That's sort of a question for sociology.
Well, it was a rhetorical question, but the original Dyson Sphere, the way Dyson envisioned it, the civilization would have actually been built on the inside of the sphere, wouldn't it?
Yeah, I think so. I think you're right. And then they would mine that sphere for energy and live comfortably ever after, I guess. So. Okay, well, I think we've probably burned up your time. So thank you very much for your attention and
So I asked Fred about a shirt or a hat, and he said that he could use another extra large t-shirt. However, I did not have any in stock in my stuff. So if you could send me your shipping address, Fred, I'll have one.
Oh, well, okay, yeah, we'll just email. It's also not very important. I mean, it's very important to have Lowbrow shirts, but the urgency is not very important. So whenever we get to it, it's cool.
Yeah, just send it to me and we'll get it to you.
Okay, now
most of the stock is up for the treasurer of Traverse City. That's why we would ship it. So.
Okay. On a more practical question, if I turn off my computer, are we going to lose the Zoom people? No. Okay. So someone else is host. Okay. I didn't want to. Okay. See you all on Zoom. Thank you. I didn't want to. I didn't want to unplug people.
Right. Okay.
Oh man, I have 25% battery left, so that didn't use a lot of battery.
But we made it.
But we made it. So.
Yeah.
Yeah.
Okay.
Zoom plus PowerPoint eats up more energy than PowerPoint.
Yeah. Well, you're using a lot of stuff: microphone, camera, speakers. Yeah, it's using it all. So. So at this point, I would like to see if Jeff could make Harry Anderson a co-host. He wants to share his screen. And this item is about some conversation we had about ACNO events.
Well, thank you guys so much.
Thanks again. And a conversation started about somehow changing the name of those in honor of John Coslin. So there were some various ideas thrown out there, and what Harry has shown us here is what he has gathered from those. So go ahead and take it away, Harry.
All right, sorry, is that big enough for everyone to read it?
Oh, yeah, you're right.
You guys can hear me okay, right?
Yeah, bear with us just a minute here. Yeah. Here.
Oh, that's bad. Sorry.
I'll carry it around everybody individually. Yeah.
You hit the button. You want to update right now, don't you?
Are you putting it up on the big screen?
I'm trying.
Run that system mechanic on your computer.
I've never plugged this thing in this way.
Well, I guess while we're doing that, obviously there was an Any Clear Night Observers Night that was recently held. And so the thought was, since I know that Mark and John actually were the ones that created the ACNO acronym for Any Clear Night Observers, which often happened on John's driveway. The question was, should we maybe change the name a little bit so that it would reflect and honor John, since, you know, that his passing obviously is most notable to all of us, but it would give us a little bit of permanence to what he created for the group and for the organization and for all of us. So, you know, the ACNO is the current acronym, but there were a couple others that some of the others brought up, and I don't know if it's up on the screen. I tried to attribute a few of the names that people, I mean, Adrian and Jeff thought Coslin's Nights might be one option. And Debbie actually piped in that John used to be named Jack when he was small. So Jack's Any Clear Night Observers, or JACKNO, was one of the suggestions that a couple of folks kind of came up with. Or John's Any Clear Night Observers, JACNO again. And then we had Coslin's Clear Night Observers, Any Coslin Clear Night Observers, ACNO, or Coslin's Any Clear Night Observers, CACNO, CACNO. So these are just some of the ones that came across on the email chain when people were responding. So I thought it might be good to put those out there. If you guys have them up on the screen, and just people might want to think about what would be best and make everybody happy, and maybe we can vote on it or something like that. Yeah, Charlie, I think you're muted there too.
Our vote was to not change it and find some other way to honor John, I guess, through it. So we've got that option too.
If they can hear us better that way. Hmm. Well, that's a good point, because he doesn't have his computer here to put his screen up there.
Yeah, that's the problem.
Yeah.
I don't know where Mike is still on, is it, Chuck? Isn't it, Charlie, on here?
I know it was up.
I guess while everyone's still looking at it, I was just thinking of other ways we could generate some money for the organization. And maybe we should take the observatory kind of down at Peach Mountain, and maybe we could find a corporate sponsor who might allow us to put their name on it to make some money.
There's an idea for additional funds.
No, wait a minute.
I got lost somewhere.
That probably wouldn't fly with the university.
Yeah, I know
They
you
didn't
didn't say that.
What he's saying, I'm sorry, I missed that.
I did too.
I said that probably wouldn't fly with the university, since many decades ago they had us quit putting out a donation box because they said there was issues with it.
I think that's Doug Nell was talking. Yeah, okay, I can't.
It was.
Yeah, you're correct. I remember that donation thing, and they said no. He's absolutely right.
Mm-hmm.
That's why I'm trying to figure what they're talking about, finding a donor.
Yeah, it was an idea for, raising more funds for Lowbrow. I can tell you, just membership dues alone.
What if I have Harry email you that?
Money has been
Then you
coming
can
in
inject it.
steadily.
Oh, yeah, just look at the report.
Yeah.
That's all you have to do. Figure it out.
Harry, could you, we gotta work the kinks out of this. Could you email that list you've got there to Jeff? If you send it to him right now, then he can put it on the screen here for us.
Okay, we'll do that in just a second. I mean, were there any other additions, and I can type them in on here?
I think those are some pretty good options.
We're good with this?
Yeah.
Give me 1 second.
Mm-hmm.
Yeah, part of the problem was that it wasn't looked into the lecture PC, so they were not showing what came through the actual.
Yeah, next time I think we got to fire up that one again. Yeah.
Yeah, you have to log in. A little surprised because Fred's LSA, but he might be version on their lecture.
All right, coming your way.
And thanks for doing this for us. Appreciate it, Harry.
If you could stop sharing, Harry, that would be good.
I guess I could also put it in the chat too.
Yeah, I can't do that with this version. Hey, Harry, can you stop sharing, please?
Yep.
There we go. Desktop. Do you see that? No. Zoom is sharing my screen. Maybe I need to share the other screen. Let's try that.
So experiencing technical difficulties. I remember hearing no, leaving it at no, but calling it puzzle nice were some of the more popular or being market. It's an act no night, it always will. So thinking those are the front runners. How much interest there in change from the regular? The quickest solution would be to say,
I don't know what this is
it's all
doing.
good, but we're just gonna call it ACNO.
Yeah, right projector, left
John,
projector.
we have it in our hearts anyways. But we leave it ACNO and mark the corrections happen. So I'm writing that down as one of the options. I second that. And that one has been seconded.
Call it a John Ackno.
Yeah.
Call it a John Ackno instead of like a Jackno.
So let's get all the options and see if they're what kind of interest we have in all of them. Which is in Osland.
Hey, Jeff, I put it in the chat too if you need it from there.
Okay. I can't get it to project. Built-in display.
But adding the C in front.
Here, I think you're doing it now.
It says I'm sharing your screen, but it's on there.
You're up.
It's just like I can see the next blank screen. There's I can see my cursor over there.
Who is it? Who likes the idea of making it a techno? Putting Osmond in front of any clear observer, night observer. Do we have anyone? Going once, twice. Techno has no support. There's, what was one of the other ones, Harry? There was Cosland Knights.
Got Jack.
Jack, no. Let's go with Jack, no. John's any clear night observing, or J. John Cosland. The name Jack No sounds cool, I think. Any support for Jack No's? On Zoom or in the room?
Yeah.
We'll be here all night.
Wireless presentation.
So I'm not seeing support for Jack No's either. And I remember the one that I suggested was Cosland Knights. But that would change the name from ACNO. ACNO would be in parentheses or something. And it would be Cosland Knights. It would go out as Cosland Knights. We're going to observe such and such. And oh, there we go. So CACNO's been. Oh, and your mic is on. Let me do this. Where's your mic? All right. Can anyone on Zoom hear me without that echo?
We can hear you now.
Okay. We figured out how to stop the echo. Doug Warshow, it's whether or not we're going to rename.
Recording in progress.
It's whether or not we're going to rename the ACNO night in some way to honor John Cosland. The John and Jack City Clear night. There we go. Now you guys can see it and we can see the screen, so I can read it from there. Okay, so we went through CACNO. We didn't get any support. I'm just looking to see how many people we have support for. We have support for just leaving it as the original ACNO night. We had someone in the room second that. The second one, Cosland's Any Clear Night Observers. I'm looking for someone who would actually support that. If we don't have anyone else that likes that idea, we're going to take it off the table. We're seeing folks that supported the other ones on the screen now, so I don't have to mention those. All right, Doug, you're voting for any of them, so you don't count.
Stuff on the ballot box.
Yeah, that stuff's the ballot box. We want a strong, like we had the second for just leaving it as an ACNO. Any Cosland Clear Night Observers? Anyone like that one?
Yeah, I like that one. It's Harry.
ACNO, well, I'll just mention that we do have any Cosland Clear Night Observers.
Yes.
So we have one person, I think that's you, Harry, isn't it?
It is, yes.
All right, Harry, I'll put you down. So that one's in play. And then Cosland's Clear Night Observers, CCNO. Any support for that one? All right, CCNO is out. So quick summary, Any Clear Night Observers, leave it as is in. We have support for ACCNO, Any Cosland Clear Night Observers. We have support for, well, Cosland Nights is myself and Jeff. John's Any Clear Night Observers, Doug Scoble, Debbie Smith. Jack's Any Clear Night Observers, Debbie, Doug, and Barry. So there's actually more support for, there's support for Jack now, which is who we name it after. Is that after you, Jack, or is that a different?
No, it's not after me, I'm not sure what.
It's just John, J and John in here, but yeah, it could be confused, I suppose.
Well, so JACNO itself is still it's an acronym that's in play. Okay, so we have the. Let's see, so I have 3.
So people are all voting on the chat.
Yeah, we have to do ranked choice. I like that idea, Kurt Hillig. Ranked choice voting. So that there are 4 options here, and I guess ranked choice voting would be the best. I'm gonna make JACNO just I'm gonna combine that one because it's JACNO either way. I don't know if there's a preference for Jack or John.
Okay, cool.
Favorite planet to observe is the Earth because I live on it. I'm just saying. Okay, so
who brought up
do we want to do the ranked voting tonight, or we want to have people email their ranks and count them? Because we could be here a while if we do this.
Better email.
And
Let's.
1 through 7. Don't spell it out.
Well, we're going to limit it to 1 through. So 1, 4, no, 1, 5, 6. I think it's 1, 4, 5, and 6.
On the other hand, Jeff is firing up a hole there.
No, I don't know where that came from.
Oh, really?
I didn't fire it up.
Yeah, look at it, Jupiter and Saturn. What about Uranus? What about that? Anyway, so what we'll do, so those that are interested parties, let's do a ranked voting, and we're going to limit it to leaving it as any clear night observers, any Cosland clear night observers, Cosland nights, or JACNO, John or Jack's any clear night observers. Those are the 4 choices, and we would like you to send an email to, what do you want to send it to me?
The whole flow? Well, that's gonna.
No, I'll be happy to compile them. So
Okay, to Harry.
Yeah, because you were doing it anyway.
Yeah,
Are you
so
gonna send this out to the whole membership or only just?
only Harry Anderson.
so I'll send out an email. We have the 4 choices. Just Adrian, send me the 4 choices. I'll send it out to everyone. Just reply to it and put your choice in there for the 4.
Send it to
That'll work.
That works. Let's go.
And
Next issue.
We'll give everyone 24, 48 hours or something like that if that works.
so just to recap, the 4 choices are the original ACNO, as named by John and Mark Press, the ACCNO, the JACNO, because we can pronounce that, or calling it Cosland Nights. So I would rank those in terms of 1, 2, 3, 4. If there's one you do not like at all, just leave it off of your ranking. Or Harry, if you prefer everyone, rank all of them, go ahead and run with that show. And we'll find out if we're going to change the name of our ACNO nights.
Okay, I'll send it out shortly.
All right. Okay, much appreciated, Harry. All right, that brings us to officer reports. I only have one item, and that is I got an email from a person that works for the U of M Retirees Association, and she was asking about getting a tour of the Peach Mountain facilities. So I explained to her that there really wasn't much that we could do as far as a tour because we only have access to one building. So, but I did explain that we do a really good job of giving people tours of the night sky and encourage them to go that route instead. But on the other hand, I didn't think we were going to squeeze that in this year yet. So I advised that she contact us again in March and we'll see if we can set something up. And then she came back and said, yeah, that would be fine. She'll contact us in March when we start doing tours again. So hopefully we'll get that misunderstanding cleared up. But anyway, that's all I had. So I will go to Liz. I think I see you there out there.
Yep, here I am. Hopefully everybody can hear me.
Yep.
I'm never too sure about my internet connection, and I'm extremely dubious about Zoom, but anyway, hello. Yeah, I have a couple of things. Number one, I have the keys to the mountain. So if anybody needs them, I've got them. Number two, RASC publications. Of course, this is all being the overall coordination is Doug, our treasurer. I have the handbooks. We are still waiting to get the calendars. And of course, distribution will occur when all components of orders are in the same vicinity, i.e. my house. So we're still waiting on the calendars. And I know that Doug is kind of going a little bit back and forth. So I will defer to his updates. And finally, I did email Professor Dan Crane, who was a Lowbrow member in the past. And I asked him if he could recommend someone who might be interested in speaking to us about space law. And he said he wasn't familiar with anybody at our shop on Central Campus, but that he was today going to have lunch with members of the Space Law Institute, and that he would get back to me. So hopefully I will hear from him in the coming week or the coming couple of weeks, and hopefully get a presenter on space law lined up for next year. And that's my report. Thank you very, very much.
Yeah, so the space law was in the news because the Russians sent a missile up to take down one of their satellites as some sort of demonstration project, except it sent debris hurtling every which way. And
absolutely. Mm-hmm. Yep, exactly. And with Virgin Space, Galaxy Quest, whatever the commercial outfits are now, this is something, of course, that's its own sort of developing story, right? So it's an interesting and a very dynamic occasion for people who practice space law, something I'm not even all that familiar with, you know. I mean, are there space law courts? Who knows? And that's why, you know, hopefully we can get somebody to present on it. I see Kareem has posted there about RASC. Okay, well, there you go. So it's the general distribution situation. So, you know, we hang in there.
I just want to point out this was never a problem till Adrian joined RASC.
Oh, okay. Okay. It's Adrian's fault.
That sounded like an admission of guilt to me.
No, it's not. And by the way, I'm going to jump in, and I guess it'll be part of my report.
I've lost audio.
I heard you, but I'm not hearing anybody else.
Kareem's got his microphone muted. That's
Yeah.
why.
There we go. There we go.
We'd love you to give a quick intro of yourself.
Tell him to unmute him. There you go.
Hi, folks. I'm Kareem. I'm here in Montreal. I'm a prof in John Abbott College here. It's kind of a junior college level, last year of high school, first year of university up here. I teach physics and astronomy. This is my wife, Karima. Not intentional, it just happened that way. Our kids are Ilyas and Tara, and Ilyas was on earlier as well. We're all together pursuing the hobby as best as we can up here with the Montreal Nebula and the clouds. And I got to know Adrian through the Global Star Parties, which has been a blast. I've been involved in outreach and public event coordination and education in the high schools and with the Girl Guides and the Scouts for about 5.5 years with astronomy, and before that with just science and physics in general. So loving all of that. And then everything you talked to me about with the Lowbrows, I thought that this is a great community to be part of. So we're happy to be Lowbrows.
I'd like to point out that the Lowbrows beat was as a potential member. He liked but David Levy scared him away. That's what it really was. But
David Levy is our honorary president. He grew up in Montreal, so we've known him for a very long time. And I know he's part of WASP, but just reading a little bit about the types of events and the speakers, and especially the outreach that you guys do. And we thought that if we are able to cross the border, it'll probably be around the Windsor area. So that would be where we'd want to come.
Yeah, and in turn, I'm in the Sarnia, and Jack, I don't know if you're still
London Center.
Which one?
London Center, RASC.
Jack's in London. So there are a couple of rascals here to keep you entertained.
Excellent.
You're slowly taking over the Lowbrows, apparently. So thank you, Kareem, and welcome to our group.
Thank you so much.
Welcome aboard. Okay, with that, Adrian.
That and
is that your report?
The lunar eclipse, got a chance to take pictures. You all saw. That's my report.
Cool, thank you. Joy.
Just that I updated the calendars to reflect that it's now in person and still the other.
Okay, thank
so
you.
that's it.
So, hybrid.
How about Jack?
Okay, was out at the observatory today doing some more just maintenance on the observatory and testing the right ascension drive and the declination drive and things like that, because we haven't been using it that much, but I wanted to just make sure that things were functioning out there. Another thing we did do is through the Michigan Dark Sky Group, they had a lecture, Reducing Light Pollution, out in Osceola Township, which is out in Howell, Michigan. I went to that and talked to the gentleman who was active in getting the, his name was Robert Parrish, and he gave the light pollution talk, but he was also active in getting the Dr. Lawless Park as the new International Dark Sky Park in Michigan, part of the Michigan Dark Sky Preserve. So it was interesting because next year they've got some other programs going out at this Dr. Lawless Dark Sky Preserve, and there's a few local community colleges that are looking at the idea of maybe having an observatory built out there. So it was kind of interesting what he talked about. Other than that, that's all basically we've been doing is taking care of the observatory and just waiting till things change for next year. And
what was the gentleman's name?
His name was Mr. Robert Parrish, Parrish. He's from Edwardsburg, Michigan, and he's a member of the Kalamazoo Astronomical Society and the Michiana Astronomical Society. But he's a delegate to the International Dark Sky Association for the past 5 years. So he's been working a lot in that area of Michigan Dark Sky Preserves and things like that.
I have to tell them to start looking up at the thumb. There are some places there that ought to get some consideration.
Port Austin is one of them up there in the thumb. Port Crescent, I should say, is one. And they've talked about a few other places, but I know Port Crescent had a lot of people supporting it. We were up there for the inauguration when they had everybody up there from the state senate and all that were up there. There's a few groups on that.
There's a lighthouse park that's actually a little bit darker, but they've started adding a bunch of lights.
Well, that's the whole argument behind it and everything that you have to do to keep it a dark sky area and that. So that was very interesting. The only other thing I was going to ask you is about taking Young Astronomer and could we put it on our Facebook page?
I think we just have it. Yes, we can.
It should be on, when you go to the page, you see it there.
Yeah, I think we have it as a website in the About Us, but we can make it more prominent.
Yeah, I would like to see it prominent on, so when you go to, somebody just goes to Facebook and you get that main page. I know there's a lot of other ones we have, but that would be good to have that on there.
Okay.
Should it have its own Facebook page too, and then it can direct you back to the other, keep moving them back and forth?
You'd have to have somebody really running it. I mean, because
it would just be a matter of setting up a Facebook page. That's,
yeah.
We set up the general.
My idea was the lowbrow one, and then having it on the lowbrow one, and anybody going there would automatically see that and be involved with it.
The easy way is to put it right up front somehow, and then have people be able to click there and go to a website.
Yes.
The other thing would be to have a Facebook page and then include the website and start a community with it. So there's a couple options.
Okay.
I don't know if anyone heard me on we have two options: create a Facebook page or just put a link in our current Facebook page to the Young Astronomer website.
Yeah.
If we started a new Facebook page, we could create a community and have Young Astronomer grow that way through social media. So those are some options we'll have to keep in mind.
Okay. Yep, that's about it.
Thank you. Jeff.
Tonight, 20 online max and 11 here in attendance. Other than that, I think Krishna's report pretty much had the summary of whatever's going on for the web and other things on the communication committee. So I guess I don't need to hate them. I can't think of anything else to really report other than that. So, okay. Other than we have to use this lectern PC next time around, otherwise chaos ensues.
Yeah, we're sorry for not having a smooth one this time. It was probably smoother the last time, but the reason is we thought for a minute we were going to get away with it, just using Fred's laptop. And before it was too late to mess everything up, we discovered it wasn't working very well. Too late. So anyway, we'll clean up our act. We did get a report from Doug via email. Let me just work my way through that a moment. Yeah. If I find it before you, I'll. Okay, so our treasurer, Doug, reports that we have 173 memberships, including a new member from Quebec, who you just met, our first international member. This count also includes about a dozen memberships that would have expired, but for grace extended due to COVID-19 pandemic considerations. We have $11,581.57 in the treasury. About 400 of that amount is money owed to the RASC for the 2022 Observers Handbooks. RASC 2022 Observers Calendars and Handbooks have been ordered. We have paid for the calendars, but we're still awaiting their arrival. The handbooks have arrived, but we're still waiting for the invoice from RASC so we can pay for them. Vice President Liz Calhoun has graciously accepted responsibility for distributing the items. Since our October meeting, our expenses consisted of payments for our usual monthly newsletter publishing and printing, or printing and mailing. Our monthly fee for maintaining our open house telephone hotline, and reimbursement to Observatory Director Jack Brisbane for observatory expenses. And that is Doug's report. And also Krishna, I got this up on the screen there. Oh, okay. Can everybody see Krishna's report?
Yeah.
Good, I'll let you read it because it's long.
There will be some cutting and pasting going on with that,
yeah.
and some of these others as well.
Yeah, basically the website's been updated with the minutes, newsletters, and young astronomers observing calendars. It's now updated officers' information, whereas previously some of the phone numbers were missing. Haven't posted the communication meeting minutes, but I got him the share URLs for that, so those should be forthcoming. And we're still exploring the web transition plans and whatnot. And he's hoping to add a weather widget to the website and possibly a clear sky clock for each mountain. COVID update, numbers are going up, but vaccination and masking are working well as do the outdoors. I did read today the president of the university, Schlichtel, was saying that Washtenaw County and southeastern Michigan in general are going to be coming under more severe threats. So expect mandatory masking indoors and things like that. Right now, but they're climbing elsewhere because people haven't. Somewhere I can bring. Anyway.
You take your word.
It was a very long email, but that was the gist of it.
Yeah, if you want, send it out to the membership if you haven't done that already. Then we can
get your flu shot. That's his other message. Saved it already. I saved everything.
Okay.
So sorry. Christmas.
And that's all the officers that are here tonight, one form or another. So does anybody have anything else they'd like to bring up?
For the news, on behalf of the newsletter, I think it came out, good newsletter came out recently, November. So are those are just emailed to the membership, right? And
there's a few of them that are mailed.
That get mailed out. Yeah. So if you haven't checked for it, I know there's an issue that was raised about folks that couldn't get their newsletters. Doug Scoble sent an email to the membership addressing it. So if you didn't get the newsletter, look for Doug Scoble's email to the membership. I think he mentioned some things to checking spam or things like that. So other than that, yeah, the newsletter is out.
Look great.
And it looked great.
Okay. Anybody have anything else? Then Jim? I thought you.
Got to unmute. Yeah, just one thing for our new Canadian members. Our webmaster is an MD virologist, Krishna Rayo, and so when he says get vaccinated for whatever, you go and do it.
Don't worry, we're very careful up here. Not all of us, but at least we are.
Yeah. Good to hear.
I would bet you that Canada's vaccination record is better than the US's if I just had to take a blind stab at it. But
unfortunately, not all the provinces, but luckily the ones that you're closest to, yes.
There we go.
Okay. Well, with that, then, do I hear a motion to adjourn?
Motion to adjourn.
Motion to adjourn.
We have
support.
Motion and support. So with that, I assume nobody's opposed. And thank you, everybody, and we will see you next month. Just one last thing. I hope everybody has a very pleasant Thanksgiving next week. and thank you.
Thanks, Charlie.
Thanks. Good night, everyone.
Bye, guys. Thanks.
Thanks for your patience.
Say, get the bullet, try to follow in the one.
All right.
I did it successfully.